Okay, Thanksgiving's coming up. Quiz. Turkey comes out of the oven at 170 Fahrenheit, and that's 100 degrees warmer than the kitchen. So we say that the temperature of the turkey relative to the temperature of the kitchen is 100 degrees Fahrenheit. The reason we want to talk about the relative temperature is we want to talk about how the temperature approaches the temperature of the kitchen. So we're not interested in how many degrees it is on the Fahrenheit scale. We'll do it on a scale relative to the temperature of the kitchen. Okay, after 20 minutes, things at 130 degrees Fahrenheit, and that's 60 degrees Fahrenheit warmer than the kitchen. So we start at a relative temperature of 100. In 20 minutes, we drop to a relative temperature of 60 Fahrenheit. First thing, take a graph of relative temperature versus time, slap a scale on it, and plot 2 points corresponding to the information I've given you. Then, assuming that the turkey approaches room temperature exponentially, which isn't really true when it's really hot and evaporating a lot, but we'll pretend it is. Okay. Assuming the relative temperature is an exponential function, we can make that exponential function in one of two forms. We'll just use the AB to the T form instead of the AE to the KX or KT. Okay, you've seen that form, but the AB to the T form is a little easier to deal with right now. We'll see how to do the other form as well. Anyhow, we find A and B, so then we'll have a model. And then if we're going to serve this thing when the relative temperature is 50 Fahrenheit, which means turkey's at 120, okay, which is about as hot as anything you want to bite into. Solve, find when to serve, okay? Okay, we can't spend too much time on this. So there are a few little glitches I've seen in people's graphs. We start with the graph, and initially, the relative temperature is 100 Fahrenheit. Relative temperature is never 170 Fahrenheit, okay? That would put the turkey well over boiling. It'd have to be superheated, okay? Relative temperature is 100 Fahrenheit. So I would start by just drawing a line here for P relative equals 100, okay? And then I would put a point here corresponding to, that's when we're going to start timing it. No point in starting to time it before we take it out. Although maybe our clock was already running and we do have to write down time, okay? But we can always shift our graph to the left so that our T equals 0 occurs at the time we first observe the temperature, okay? So I would start that way. And then you have 20 minutes. What's 20 minutes? Well, we're going to draw a vertical line for T equals 20 minutes because time is measured on this axis. And we don't want to draw 20 minutes way out here because it might take a couple hours for the temperature to come down to what we want. Okay? So we'll probably put 20 minutes at a comfortable distance from the axis, but not right on it. And then we'll figure out where to put the point for T equals 20. Okay. Well, I'm going to give you that much also. There's 100, 50 would be here, 60 would be about here, because I've told you that the relative temperature at T equals 20 is 60 degrees. Okay. Now, if you're really good, you can sketch an exponential curve here. You know the temperature is going to approach, the relative temperature is going to approach zero. If you leave that turkey out long enough to get yourself really sick, it'll come down to room temperature or very close to it. Okay? I advise you to put it up a little bit before that. Okay. Hey, don't leave it set out too long. So there's a picture. You kind of know what the graph is going to look like, but you don't have the details. And now you've got to write this equation and then plug your information into the equation so that you can figure out what A and B are. And that's exactly what you would have done, I think, if you followed the procedures Open Math gave you and that I gave you. Okay? Well, they show you a curve and ask you to figure out the function. And usually it doesn't have a nice asymptote at T equals zero. So at relative temperature equals zero. Okay? So I'm giving you a nice asymptote to make it as simple as possible. So if you follow the procedures, you're going to get two equations that you can solve for A and B. Okay. And actually, you don't need to do simultaneous equations because one of the equations will tell you what one of those variables is, and then the other can easily be solved for the remaining variable. Okay. Now, once you have the graph, each point gives you an equation. Each point can be plugged in, the X and Y coordinates can be plugged in here. So now from the graph, you could just say that what's a 0.0100 mean? It means that when T equals zero, big T is 100, right? And let's call that T relative. I always scribble something down there so you know I've got a subscript on it. Okay. Well, T relative of T is AB to the T, so T relative of zero is AB to the zero. That equals 100. Now we don't need to know T relative. Right here we have an equation that we can easily solve for A. It says A times 1 equals 100. So A equals 100. All right. Well, okay, got it. All right, so we know that T relative of T equals A, B to the T. A equals 100. So T relative of T equals 100 b to the t. Now, we also know t relative of 20, meaning at 20 minutes, equals 100, b to the 20th, and t relative of 20 equals 60. So here's an equation that we can solve for b. First, we just divide both sides by 100. I'm just deciding how much room I have, how much detail I want to show. I'm just going to put 3 dots there. You should fill in with the details of the step where you divide both sides by 100, that everybody knows to divide both sides by 100. And everybody knows you can. I'm just saying, yeah, that's what you do. You get b to the 20th equals 0.6. And then you solve for b. Now, how you do it using exponents, because even if the exponents are a little confusing, people who haven't had algebra for a while don't necessarily remember how to use roots. You could say the 20th root of 0.6, you know how to do that, it's okay. But you should understand the 1/20th power. We're just taking the same power of both sides. And b to the 20th to the 1/20th is b to the 20 times 1/20th. And 0.6 to the 1/20th is approximately 0.97. So b to the 1 equals 0.97. So b equals 0.97. These are steps you don't want to skip when you're writing things out, because you get into an exam or need to use it later and you're not used to writing out the steps. You don't remember what steps to skip. So you do something superstitious. Okay? And that's going to happen the majority of time to the majority of people. So we write this out very completely. Then we can kind of summarize. So now it's only approximately equal to 0.97. I had the approximate equal up here, but I'm going to keep it throughout. Okay, b is approximately 0.97. So our function is big T of little t, and we'll do the subscripts, t relative of t. And it's 100 times 0.97 to the t. We still haven't answered when t relative equals 50. Okay? But we've got all this. It all went into 2 equations, this equation and this equation, which we easily solve for A and B. Maybe not so easily, but the solution for A is easy. If you let your first point be the t equals 0 point, this one is always easy. A is going to just be whatever that is. But don't skip that step, write it out, because sometimes you don't know what the t equals 0 was, okay? Sometimes Well, that's the point. Okay, we got a question. Let's see what we got. Okay, so let's go ahead and figure out and it's usually helpful to write out the units, degrees, or minutes, so you don't get confused, because that was the source of the question we just had. Just somebody plugged 50 into the equation here and got a perfectly good answer and told us that what the temperature would be after 50 minutes. Now, that's perfectly good information. It could go right on your graph, but it's not what the question asks. The 50 was not temperature. 50 was the temperature, and what we're trying to find is how many minutes it takes to get there. So, well, and this is an approximate thing because a 0.97 is a round off, okay? If you wanted it more accurate, you go about one more significant figure. Any more than that would be ridiculous because turkeys don't behave that well. Okay? And just due to turkey misbehavior, you have a built-in uncertainty. And three significant figures on this number would predict the turkey about as well as the turkey is going to behave. Okay. Now, so I can write it out like this: T relative of T equals 50. Okay. Well, T relative of T equals this, and it equals this. Okay. There it is. Now, you know how to solve that equation. Can you solve that equation? Give you just a couple of minutes. Okay. Now, people did pretty well with this. I mean, everybody got down to divide both sides by 100 and you get 0.97 raised to the T equals 50 over 100. So 0.97 to the T equals 1/2. Okay. Or 0.5 since I'm going to write that out separately so we can translate it. 0.97 to the T equals 0.5. And now you got to find out how many times you got to multiply 0.97 by itself to get 0.5. And the only way you got to do that is to use the equivalence that we talked about last time. B to the A equals C if and only if A equals log base B of C. Okay, so you take this equation is in either this form or this form. Somebody tell me which form it is. This one or this one? Top one or the bottom one? Look at this equation, look at this, look at this. Yeah, it's obviously in this form, right? And what's the value of C? You show me with your fingers. If this equation is B to the A equals C, what's the value of C? Yeah, 0.5. Yep. And that showed me enough. I knew you saw it. Okay. And what's B? It's 0.97.
Yeah.
And what's A? Yeah, you could have done this. Okay. Okay, does everybody see that? This is the form. Okay. It's this form with these numbers. Meaning you can write the equivalent equation in this form. So what is the equivalent equation? What is A equals log B of C? Write out that equation. Okay, so we write out this equation using the A, B, and C. A is T, so we write T, replacing A, equals log base B. B is your 0.97, and C is your 0.5. Okay. Then using the rules of logs, which we talked about last time, this is the log of 0.5 over the log of 0.97. And you have LOG button on your calculator. You also have an LN button for natural log, which I told you about last time, but it's worth repeating. And you could use natural logs here if you want. I don't have time. I don't have room to write those out. Okay. And you get approximately 23. Okay. 22.7 or something like that. Now, remember the 0.97 should have at least another significant figure to get a little more accurate on that time. It might make a difference of a minute or two. But the method is correct. And we're just using the rules for logarithms to solve an exponential equation. This is an exponential equation because your variable is in the exponent. And you can't get to that variable except using logs. You change the form, and now your variable is right there where you want it. It tells you what it's equal to. All you got to do is know that log base B of A is log A over log B, or natural log of A over natural log of B. Now, if I sketch a reasonable exponential curve here, this tells me that T relative equals 50 is going to be just a little bit below T relative equals 60, right? So if I look at this point on the graph, the point where relative temperature is 50, and project down there. Well, I'm thinking that on the graph, that looks like maybe T equals 25. In other words, if this is 20, then 10 is half of that, and 5 is half of that, and that looks pretty close to 5, maybe 4 or 5. But that's just my hand-drawn graph with my version of an exponential function. If I constructed this exponential function in a rectangle to make it more accurate, I could come up probably with an even better estimate. Or if I went to 3 significant figures on my 0.97, I could come up with a better estimate. Okay? But it does make some sense. Now, another little plug here. This is a connection that I hadn't planned on doing, but it's pretty simple. What's the average rate of change of your relative temperature with respect to time between t equals 0 and t equals 20? Does that ring a bell? Because it sure should, because it was on your test recently, and everybody that took it, did at least decently on it, I think. The rise divided by the run. The rise is from 100 down to 60. That's negative 60 degrees Fahrenheit, and the run is 20 minutes. So that the slope is 60 degrees over 20 minutes, which is 3 degrees per minute. Now, the slopes are decreasing here. If the time is 23 minutes, let's say here, then in 3 minutes, the temperature went down by 10 degrees, right? Temperature goes down 10 degrees in 3 minutes. How many degrees is that per minute? I mean, that's the slope of the graph. That's, rise over run. The rise is negative 10 degrees. The run is 3 minutes. That's 3 1/3 degrees per minute. We said that the average rate of change from this point to this point was negative 3 degrees per minute, and now it's negative 3 1/3 degrees per minute. It's not going down faster here than it is here. Does that make sense? So if you think it's 23 minutes, then you think it's going down faster here than it was here, and that's not what's going to happen. The physics of it is simply that the more difference there is between the temperatures, the more heat comes off. Okay, that's not a difficult concept. Which means that the temperature is going to be going down at a greater rate when the temperature is higher. Just a little connection to understand maybe why we want to understand exponential functions and some of the things that we can understand about them. So one way of checking whether that answer is reasonable is check whether your slope is reasonable. Okay. So I'm thinking that 25 minutes might be better than 23 minutes, because then you'd be going down at about 2 degrees per minute. Okay. And if you redo this with something more accurate than the 0.97, you're going to get a little different answer here that checks out and which the rates check out. Okay. Yeah, that's kind of a neat connection. I'm glad that came up. Okay, I'm not going to talk any more about that, but after you leave, I'll probably do a little addendum on the end, just talking a little more specifically about these rates, because it's something you should understand. There could be questions on the exam where you would look at those rates, because the way rates behave for exponential functions is very important. Okay. I want to construct these 3 graphs, all graphs based on the log base 2. First of all, let's sketch a graph of the base 2 log. X equals 1. Y equals 0. When X equals 1/2. y equals -1. Now you can get this graph. This is y equals log the base 2 of x. You can write a table for the base 2 log and reverse the columns and get the graph. Or you can think it through in your head if you're real familiar with that graph. I'm not going to write it down. I'm going to let you write down the table and show that these points are on the graph. But anyhow, then when x equals 2, you have y equals 1. And then to get y equals 2, you're going to need to come all the way out to x equals 4, which needs to be twice as far from the y-axis as x equals 2, okay? So you need to construct the lines kind of carefully. You could start with x equals 4, cut that in half, cut that in half, cut that in half. Okay. Then there's another point that you would use from the basic graph, which would be x equals 1/4. And I'm not going to label that, but you get a point down here. So your curve looks like this. So there's y equals log base 2 of x. Now, what about the graph of y equals log base 2 of x minus 3? Well, log base 2 of x minus 3 shift that graph -3 units horizontally. Now, if we shift the y-axis -3 units, well, 2 is here, 4 is here. That's 3, -3 units would be about to here. And there's the line x equals -3. And that line shifts y-axis -3 units. It takes this whole graph and shifts it -3 units. This graph has an asymptote at the y-axis because the exponential function, the 2 to the x function, has an asymptote at the negative x-axis. If you reverse the coordinates and think about it, that becomes sort of obvious. Okay. Every one of these points moves 3 units to the left so that x equals 4 point, the y coordinate doesn't change because you're moving horizontally, but the x coordinate becomes -1, it becomes 1. So that this point moves 3 units to the left and ends up here. This point moves 3 units to the left and ends up at, we'll figure it out in a minute. I'll say, because what's the coordinate of this point? It's x equals 2. If we move the x equals 2 line 3 units to the left, it goes, well, 1 unit takes it to x equals 1, another unit to x equals 0, another unit to x equals -1. So it's pretty clear that this moves 3 units to the left. So I just put a -3 on each of these arrows, just indicating what they do. The x equals 1 line moves 3 units to the left, and that's going to put it on the x equals -2 line. Then this point moves 3 units to the left. It's halfway between the y-axis and x equals 1 line, so it'll end up halfway between the x equals -3 and x equals -2 line. And then this point will move over to where it's only a quarter of a unit to the right of the x equals -3 line. And there we've got a graph. It has exactly the same shape as this graph if we've constructed it accurately. And that's going to be y equals log base 2 of x minus 3. Now, if we want -3 times log base 2 of x minus 3, we've got to multiply all our y values by 3 and make them negative. That means that y equals 2 is going to become y equals -6. So let's see, if that's 2, then here would be -2, that's about right, -4, -6. So this point comes all the way down here to y equals -6. Okay. I'm not going to do every point, but I'll say that this point is at y equals 0. It's going to stay at y equals 0. So this point's going to stay where it is. This point's at y equals 1. Multiply that by -3, we get y equals -3. Well, if this is y equals -6, then -4 would be about here, and y equals -3. Nice labeling here. I should have labeled my x coordinates a little bit lower. Okay. But this is the line y equals -3. And this point where y equals 1 will come down here. Okay. So now we've got these points and there's a curvature. But what's going to happen to this point? This is at y equals -1. Multiply that by -3, we're going to get y equals +3. So things are getting a little bit messy. How you doing, Ron?
Great. I was just wondering if I could come and do a plug for the Earth Music concert at 2 o'clock. Yeah, it'd be a great way to show off or
Signing to
Okay, great.
the old instruments.
Yeah. Sorry to
I've never
interrupt.
heard those live.
Yeah, just wanted to come say hey.
Yeah, there is a good program going on in the music studio. Okay. Now, what happened to my yellow chalk? Oh, here it is. Okay, so again, this point here is at y equals -1. It's going to go up to y equals 3 because -3 times -1 is 3. So we'll just draw a y equals 3 line up here, and we'll take this point and move it straight up to here. Now this point's going to go all the way up. This is at y equals -2, which I didn't label and should have. And that's going to go all the way up to y equals 6, and that's off the top of the board. Not that high, it's about there. But we can sketch a kind of a good curve here. And this is at least a section of the curve where y equals -3 times x minus 3. Okay. Now, if we do x minus 3 plus 5, that's going to take the negative y equals -6 point up to the y equals -1 coordinate, and the y equals -3 point up to y equals 2. And the y equals 0 point up to y equals 5, but that's too high. So I didn't pick real good numbers there, but that's kind of what I wanted to illustrate. So let's just do that much. So this point, we add 5 to the y coordinate, it puts us here. This point where y is -3, we add 5, we get y equals +2. I have the right point. It's this point, there it is, goes up to 2. For some reason I just wanted to put it there, that's not good. Okay, going straight up because it's a vertical shift. And then, well, it's going to have the same shape as this graph. The next point is going to go up to y equals 5. That would be the point on the y-axis. So we'll just cheat a little bit and say that's up about here. Right at the top of the board. I think it's a little higher than that, but not too bad. That's probably about right. And we can sketch that, which would match what we get if we take this thing and lift it up 5 units. Well, that's how we understand transformations for the log graph. It's not particularly difficult, but of course, people are still a little fuzzy in transformations. So this will kind of unfuzzy you a little bit, okay? Because the transformations are something that I'd really emphasize. They're one of the central ideas in the course. Okay, I think we're on the board space. No, we got one here. I'm going to start not drawing exponential graphs, but I'll continue with it. Okay, they're exponential graphs. Those are not log-based B graphs. Your logarithmic graphs are going to be inverse to these. So you're going to have the graph that looks like this. Nice straight y equals x line there. Okay, your exponential graphs are like this when you have greater exponent. If they get steeper, on this side it gets lower. And if we do the log base B graphs that are inverse to these, they're going to look like this. They're going to get flatter as B gets bigger. So for example, log base 5 graph will be flatter than the log base 2 graph. Okay. And I said larger positive B. That's my brain. It shut off. Longer values of B that are greater than 1. Now, if B is less than 1, there's a graph, B less than 1. And I'm not going to indicate what's greater, but just a review of what the exponential graphs look like. So what the logarithmic graphs look like. In the logarithmic graph here, it'll be like this. So the whole picture can get kind of complicated. You want to be aware of that. And then you want to ask, let's say you wanted to find the vertical asymptote of y equals log base B x plus 5. That shifts the graph 5 units to the left. You know, I'm wondering if I did something really stupid here, and I did. Let me back up and correct total bonehead thing I did here. It's very easy to do. I shifted these graphs 3 units to the left. That would correspond to x plus 3. Okay. So this is how the graphs shift, but they were graphs of x plus 3. Okay. So anyhow, the graph of x plus 5, the y-axis is the asymptote, whether it's b less than 1 or b greater than 1, the asymptote is to the y-axis, and that asymptote is going to move over to x equals -5. Okay. So that's a vertical asymptote. for any log of x plus 5. Okay. So that took a little longer than I expected. Held you over a couple of minutes. Okay, good luck with the homework. And couple of sections. First one's fairly straightforward. Second one deals with the graphs. So remember what I just told you.